Imagine a miniature sun burning silently, placed beside a city inside enormous layers of armor. Around that heat source, workers remain calm, even though every deviation could carry serious consequences. Inside the core, energy is produced continuously. Outside, pressure, heat, and radiation must remain within strict limits. A plant like this requires thousands of devices, pipes, valves, cables, and sensors working in precise coordination. Even a tiny weld must be traceable, inspected, and proven to match the approved design. By ordinary logic, such a powerful heat source should not remain stable for many decades. It should exist even less within a complex machinery network where tiny errors can pass through multiple systems. If cooling flow is interrupted, heat does not disappear immediately. The system must keep carrying it away. If external power is lost, backup layers must awaken before operators even have time to respond. If a defect is missed, it may appear only after the structure is sealed and difficult to reach. Yet many plants operate steadily through repeated fuel cycles and decades of continuous inspection. That stability does not come from a harmless core, but from ensuring no protective layer stands alone. More importantly, the first layer of armor exists before the reactor vessel ever reaches the construction site. This is a nuclear power plant being built from its foundation pit, material records, and every act of verification. It must confront heat, pressure, radiation, and human error throughout a struggle lasting its entire lifetime. The demand for reliable electricity drove people to seek heat sources capable of continuous industrial-scale operation. Once nuclear fission was controlled, it showed that a small amount of fuel could produce substantial heat. Early research reactors proved heat could be generated under control, but not yet enough to power a city. The next step was turning that heat into steam, then using the steam to spin a turbine generator. In principle, electricity generation resembles a thermal plant. The difference lies in how heat is produced and controlled. Early designs quickly showed that high output required far more than a steel vessel and several pipes. Operating experience and historical accidents forced the nuclear industry to treat every safety assumption as something requiring proof. From this emerged defense in depth: prevent failures, detect them early, control them, and reduce their consequences. The operator cannot simply declare the plant safe. Regulators must independently assess every stage. Before detailed drawings, the first question is not what to build, but whether this site should be used. Geology must reveal how bedrock carries loads, how groundwater moves, and whether the ground could settle. Earthquake hazards are assessed through regional history, faults, ground motion, and the response of structures. Floods, storms, large waves, and extreme water levels are also treated as loads that could strike the plant. Cooling water must be dependable, yet the design must also consider periods when that supply declines. Population distance, transport routes, the power grid, and emergency response capability all influence site selection. The environment is surveyed before construction so later changes in water, soil, and ecology can be compared. Emergency plans are prepared early because safety does not end at the plant fence. Once the site is accepted, the first armor layer already exists, a deep understanding of where the plant will stand. Every site hazard becomes a design criterion, from earthquakes and water levels to temperature extremes. The reactor type is chosen alongside the national power system, water supply, industrial capacity, and legal framework. Within the design, fuel is arranged so the chain reaction can be controlled and shut down. Coolant carries heat away from the core, while pressure boundaries keep the fluid on its intended path. Containment surrounds the main systems as the final shell against the release of radioactive material. Important systems are usually divided into multiple trains, so one failure cannot remove the entire function. Backup trains are also physically separated, preventing one fire or local flood from disabling them all. Power is layered from the grid to emergency generators and batteries, preserving essential measurement and control. Some newer designs use gravity, convection, and natural circulation to reduce dependence on active equipment. The control room is designed so operators can understand plant conditions without drowning in alarms. Digital models reveal clashes between piping, structures, and cables before steel is cut at the site. Materials are chosen not only for strength, but also for heat, corrosion, radiation, and inspectability. Manufacturers must prove their processes, measuring equipment, and workforce are qualified before producing major components. Suppliers are also assessed because a small distant component can still become a link in a critical system. Mock-ups and training areas let workers practice operations before touching real equipment. After years of surveys and design, construction finally begins by excavating down to an accepted foundation layer. Groundwater is controlled, weak soil is treated, and the foundation surface is cleaned before reinforcement is placed. From this point, tolerances no longer live on drawings. They become real distances between steel, concrete, and rock. Every concrete pour is planned around weather, hydration, heat, transport time, and construction capability. Dense reinforcement forms the load-bearing skeleton, while still leaving exact paths for pipes and embedded components. Plates, penetrations, and anchors are positioned beforehand because correcting them after concrete hardens is extremely difficult. Concrete samples are checked for slump, temperature, and strength, so every batch carries evidence of quality. Large foundation blocks may be poured continuously, requiring shifts, equipment, and material supplies to coordinate without interruption. As concrete cures, internal temperatures are monitored to limit cracking caused by thermal differences. Finished surfaces are resurveyed, core samples are tested, and every suspicious area must be evaluated. The basemat does more than carry the plant's weight. It transfers earthquake forces into the entire structure above. The containment steel liner is assembled from curved plates, with every joint tested for leak tightness. Heavy components require dedicated lifting plans because wind, deflection, and even a few centimeters of error matter. More piping sections and modules are prefabricated, then delivered to the site to reduce outdoor work. The reactor building rises around successive structural layers, but none may be concealed before inspection. Auxiliary buildings house pumps, electrical systems, water treatment, and safety equipment supporting the heart within. Elsewhere, the turbine island is built like a large thermal station, converting steam into electricity. Heat rejection systems may use the sea, a river, cooling towers, or a combined arrangement. Cable tunnels and service channels are laid out early, because thousands of connections will later pass through them. Piping corridors must allow expansion, inspection, drainage, and maintenance access for many decades. Every construction step creates records, from material origin to the worker involved and the inspection result. At mandatory hold points, work continues only after both responsible parties and inspectors grant approval. Traceability codes connect materials to production batches, certificates, and installation positions, even when viewers never see them. When a deviation appears, it must be recorded, assessed, and resolved rather than hidden to protect the schedule. The construction site therefore becomes a system for producing evidence, not merely joining steel and concrete. The reactor vessel begins as massive forged steel sections, reducing joints and creating a more uniform material structure. Forging compresses hot steel, closing internal flaws and reshaping the metal's microscopic structure. The component is then heat-treated to achieve the required strength, toughness, and load-bearing performance. Surfaces are machined precisely so steel rings, flanges, and connection points fit together correctly. Ultrasonic waves and other non-destructive methods search for deep abnormalities invisible to the human eye. Once completed, the reactor vessel travels along a route surveyed specifically for its unusual size and weight. A heavy lift crane raises the vessel through an open roof, lowering it very slowly into the center of the structure. Supports and reference points hold the vessel at the correct elevation and alignment while accommodating design loads. Large heat exchangers are installed nearby to transfer energy into the steam-producing system. Pumps, pressurizers, and large valves complete the circulation path carrying heat away from the core. Main piping sections are aligned before welding, because installation stresses may remain for many years. Welders follow qualified procedures, while temperature, materials, and every welding pass are controlled. After welding, the joint surface and internal volume are inspected for cracks, pores, or incomplete bonding. A small signal on an inspection screen is not automatically dangerous, but it must be explained. During operation, coolant absorbs heat from the core and carries it towards steam generation or heat exchange. In many pressurized water designs, turbine steam belongs to a circuit separated from water passing through the reactor vessel. Steam expands through successive turbine blades, converting thermal energy into extremely rapid rotation. The generator converts that rotation into electricity, while transformers raise voltage for long-distance transmission. After the turbine, the condenser turns steam back into water so the thermal cycle can repeat. Surrounding the main equipment, containment withstands pressure and serves as the final boundary in many scenarios. The steel liner provides leak tightness, while thick concrete supplies strength, shielding, and protection from external impacts. Every pipe and cable crossing the shell requires suitable seals, anchors, and isolation capability. Ventilation controls temperature, pressure, and airflow direction while supporting filtration when conditions require it. The electrical system is divided into multiple buses and zones, reducing the chance that one fault darkens the entire plant. Emergency generators provide alternating current, while batteries preserve essential controls during the transition. Emergency cooling systems stand ready to add water and remove decay heat from the fuel. In passive designs, water can flow by gravity, while heat itself drives circulation without pumps. Sensors continuously measure temperature, pressure, water level, flow, and equipment condition across many plant areas. Protection systems compare signals with safety limits and can order an automatic reactor shutdown. Control rods or equivalent mechanisms absorb neutrons, rapidly reducing the chain reaction when inserted into the core. The control room turns thousands of signals into an operating picture people can understand and act upon. Before real operation, crews train on simulators to face equipment failures and abnormal situations. Control networks are segmented and protected, because modern safety also depends on data integrity. Fire barriers, early detection, and separated cable routes help prevent one fire from crossing multiple protective layers. Pipe and equipment supports are designed for vibration, expansion, and earthquakes while preserving required functions. Safety emerges when independent layers support one another, so a single failure cannot open a path to the core. As protective layers multiply, interfaces among designers, suppliers, and the construction site grow rapidly. One delayed component can block many later tasks, compressing the entire chain of work. The supply chain spans many countries, factories, and contractors, yet quality standards must remain consistent. Large forgings require specialized capability and long lead times, making late defects difficult to replace quickly. Material certificates must accompany components throughout their journey. Once traceability is lost, even good steel becomes questionable. Risk is not only a failed part, but also incorrect records, unclear origins, or inspection without independence. Welders and inspectors are difficult to replace because their skills must be continuously maintained. Long shifts and schedule pressure increase mistakes, making fatigue management a genuine safety measure. A concrete area outside requirements may require drilling, repair, or removal of already completed work. Late design changes often force related piping, supports, cables, and records to be updated together. The enormous volume of documentation may look bureaucratic, but it forms the memory of the entire plant. Regulators must remain independent from commercial pressure, political influence, and demands for early power generation. Every month of delay increases financing costs, even when the construction site appears almost unchanged. Heavy rain, strong winds, deep cold, or extreme heat can interrupt lifting, welding, and concrete work. A long project must retain experienced teams, or site knowledge will leave with the people who hold it. Language and cultural differences among contractors can turn one clear requirement into several interpretations. Configuration management ensures drawings, installed equipment, and control software always describe the same plant. Maintenance space must be reserved during design, or a small valve may become almost impossible to reach. Shielding layouts and access routes also determine occupational exposure across decades of maintenance. Systems for water treatment, waste, and used materials must exist before the plant begins producing them. Even end-of-life dismantling affects today's equipment placement, material choices, and record preservation. The armor therefore costs more than visible concrete. It includes time, capability, and responsibility that cannot be shortened. During a routine inspection, ultrasonic equipment detects a small signal in a weld on an important pipe. There is no explosion or visible crack. One ambiguous indication is enough to stop the entire area. Related work is suspended, so the uncertain component is not concealed or connected into other systems. Components from the same batch are isolated, while the quality team traces every manufacturing and installation step backward. Drawings, welding procedures, and real site conditions are compared to find where the deviation may have emerged. The origins of steel, welding materials, and heat treatment history are rechecked across the supply chain. Inspections expand to nearby welds, because one signal may reveal a broader shared problem. The qualifications and certifications of the workers involved are reviewed, not to assign blame but to identify the cause. The inspection equipment is recalibrated, because the tool detecting defects can itself produce a false signal. The question grows larger. Is this a local flaw, a procedural error, or evidence of a weak control chain? Additional inspection methods determine the shape, position, and extent of the unusual region. Independent inspectors observe the process, ensuring conclusions are not driven by schedule pressure. Every stopped day is costly, but proceeding without understanding can trade short-term savings for long-term risk. Safety culture is tested at this moment. Report bad news honestly, or soften it to preserve the schedule. The project team chooses to stop, widen the investigation, and accept delays before authorizing repair. The repair procedure is designed, reviewed, and approved before metal is removed or rewelded. The unacceptable region is treated under controlled conditions. Then the joint is rebuilt by qualified personnel. When required, post-weld heat treatment reduces stress and restores the desired properties of the joint. The repaired weld must undergo the full inspection process again and cannot be accepted merely because it was repaired. The system is then pressure tested to prove its boundary can withstand pre-operational test conditions. Containment is also leak tested, searching for tiny leakage paths before fuel enters the plant. Records are updated from cause through repair, turning one small deviation into a lesson for the entire project. After the event, welding and inspection procedures are revised to detect similar conditions earlier. The supplier receives a deeper audit, while weaknesses in material transfer and acceptance are closed. A digital weld map lets the project team see every location's status without searching through many record sets. Inspection robots can enter piping or confined spaces, collecting repeatable data with high consistency. Laser scanning records the shape of the completed structure and compares it with the model to detect misalignment. The digital model gradually becomes a lifetime twin, linking design, installation, testing, and future maintenance. Factory module fabrication provides better control over welding conditions, dimensions, and process repetition. But large modules create new challenges in transport, lifting, and final connections at the site. Passive design preserves essential functions even when external power and active intervention are limited. Elevated water tanks can provide gravity-driven flow, buying additional time for operators and emergency teams. Natural convection carries hot fluid upward and cooler fluid downward, turning physical law into part of the protection system. Diverse, separated power sources reduce the chance that one common event removes every support option. Severe accident management plans prepare for situations far beyond normal operation. Exercises test people, communications, equipment, and coordination beyond the plant fence. As construction nears completion, the commissioning team takes over each system through tightly controlled handover records. Cold functional testing checks pumps, valves, electricity, and controls before systems reach operating temperature. Hot functional testing brings systems near operating temperature and pressure while fuel is still absent. Each test adds evidence that the real plant responds as the design predicted. A reactor is not switched on and instantly driven to full power. Startup proceeds through many stages. Fuel is loaded only after structures, supporting systems, and the operating organization satisfy approval conditions. First criticality is simply the moment a self-sustaining reaction begins at very low power under close supervision. Low-power physics tests confirm the core behaves as modeled before significant heat is produced. Power rises in steps, with system checks, data reviews, and operating limit confirmation between each level. The turbine generates electricity, but is not the reactor. The two are linked by heat, steam, and protective conditions. Containment is not merely a concrete dome. It includes seals, anchors, penetrations, and isolation systems. Nuclear-grade concrete is not magical material, but a mixture designed, placed, and inspected under strict controls. The control room does not contain one red button that solves everything. Safety relies on many independent functions. Automation does not remove people. It shifts them from constant manipulation towards supervision and decision-making. Ultimately, safety is not a promise made by design, but a result demonstrated through real testing. The modern turning point is treating construction data as an asset that lives with the plant, not paperwork stored away. Data analysis can find unusual patterns across many measurements, but accountable experts must still make decisions. Drones and robots reduce the need for people to enter high, confined, or environmentally harsh areas. Construction sequence simulations reveal conflicts in time, space, and resources before the site becomes blocked. Standardized designs can reduce changes and transfer experience from one project to the next. Small modular reactors move more work into factories instead of performing everything at the construction site. Smaller does not automatically mean cheaper or safer. The entire system must still be assessed according to risk. Licensing must also adapt to modules, factory production chains, and deployment of many similar units. Passive features can reduce dependence on electricity and operator action, but they cannot replace construction quality. A changing climate requires flood, temperature, drought, and water level data to be updated throughout the plant's life. A site cannot be assessed once and forgotten. Ground movement and external hazards require long-term monitoring. Future plants may be built faster, but only if learning from deviations becomes equally fast and transparent. The strongest armor may not be a thicker wall, but a system that never conceals weak signals. After years of construction and testing, the first fuel assemblies create the heat source the entire plant has awaited. Steam begins turning the turbine, the generator connects to the grid, and verification becomes electricity for the first time. From a distance, the plant is only a dome and lights. Inside are millions of decisions that have been checked. The miniature sun has finally received its full armor: steel, concrete, evidence, discipline, and responsibility.